We present neural modes, the first self-supervised approach for learning nonlinear modal subspaces for simulation. In this example, we simulate the deformation behavior of a giraffe model made of elastic material. Full-space simulation with finite elements is generally too slow for real-time applications. One strategy to reduce the computational burden is to perform simulation not in full space, but in a low-dimensional subspace. The challenge, then, is to construct low-dimensional subspaces that efficiently capture the deformation behavior of the input model. Existing learning-based methods construct subspaces by approximating simulation data in a purely geometric way. However, this approach produces subspaces with high-energy configurations and entangled latent space dimensions, and it generalizes poorly beyond the training set. In contrast, we propose a self-supervised approach that directly minimizes the system's mechanical energy during training. Our method learns smooth nonlinear subspaces that are physically principled and offer interpretable latent space parameters. We show that, unlike supervised approaches, our method does not suffer from overfitting. We build our subspace based on nonlinear compliant modes, an extension of linear modes to the large deformation regime. Each nonlinear mode is parameterized by a modal coordinate, c, along the corresponding linear mode, L. For any modal coordinate value, the nonlinear mode shape, n, is obtained by minimizing the elastic energy in the space orthogonal to the linear mode. Our central insight is that we can train a neural network to learn the entire solution manifold by minimizing the corresponding energy across parameter space. We refer to the resulting nonlinear modal subspace as neural modes. Please see the paper for more details. Compared to existing methods based on supervised learning, our self-supervised approach offers several advantages that we highlight in the following. Our method is trained on nonlinear compliant modes and inherits their parameterization. As a result, each latent dimension in our subspace has a clear and distinguishable effect on the full space geometry. Our subspaces exhibit high smoothness and regularity. As can be seen in this interactive exploration example, smooth motion in latent space leads to smooth trajectories in geometry space. Here, we show a two-dimensional slice of the subspace. Note how shapes evolve smoothly along the latent space coordinates, but also along any other direction. This smoothness makes our learned modal subspace ideal for keyframe animation, subspace simulation, and other applications that rely on gradient-based optimization. Furthermore, neural modes are regular in the sense that interpolated geometry is semantically bounded by germinal states. By contrast, the latent space of PCA plus IEEE is interspersed with distorted or crumpled shapes that are physically implausible. Neural modes can be easily extended to auxiliary parameters that control shape and material properties. In this interactive example, we change the aspect ratio of an elastic sheet from square to rectangular. We observe that the folding direction smoothly rotates from the diagonal to the sheet's short axis in dimension 1. We additionally showcase two applications, starting with subspace simulation. We set up the giraffe model in a rotated initial pose and then simulate the recovery process. Our neural modes produce plausible motions that are qualitatively similar to the full space simulation while speeding up computation time by a factor of 600. In this example, we simulate the deformations of an elastic armadillo puppet driven by strings. We vary the length of the strings using sinusoidal functions and observe the corresponding motion. We compare with full space simulation and linear modal analysis, a conventional linear subspace simulation method. As can be seen, modal analysis leads to large distortion artifacts in the arms and legs. These artifacts can only partly be mitigated when adding 10 extra basis vectors. In contrast, our neural mode subspace produces pleasing nonlinear deformations that are qualitatively on par with the full space simulation while offering a 50-fold acceleration. In this third example, we perform subspace simulation on a bunny model and again compare it to full space simulation and linear modal analysis. As in the previous example, we observe distortion artifacts in the ears when using modal analysis. Neural modes produce smooth and visually compelling motions at a fraction of the full space simulation costs. In addition to subspace simulation, our method can also be used for keyframe animation. We create 6 keyframe poses of the giraffe model by interactively exploring latent space. Based on these keyframe poses, we generate in-between trajectories with physically plausible deformations by means of interpolation. While linear subspaces typically require nonlinear interpolation schemes to achieve acceptable results, our nonlinear subspaces produce physically plausible deformations even for simple linear interpolation of modal coordinates. To analyze the accuracy and performance of our approach, we conducted a comprehensive ablation study for our method and several baselines. We evaluated the quality of our subspaces using elastic energy, internal stress, and nodal forces as metrics. We generally observe an order of magnitude smaller errors for our method compared to PCA plus AE, while supervised learning leads to overfitting for all loss functions that we tested. Our neural modes do not suffer from overfitting. Thank you.